So, in the course of balancing a nuclear reaction, as you have it here, there's a need for me to at least expose you to the concept of radioactivity. So, anytime you hear radioactivity, the first thing that comes to your mind is breakdown, spontaneous breakdown of nuclei. So, radioactivity is the spontaneous breakdown or spontaneous disintegration of nuclei. Don't forget, you are familiar from the onset, atoms are subdivided into nucleus and electrons, after which this nucleus here, nucleus singular, nuclei plural. So definitely we are talking about the breakdown of different nucleus now. So a combination of nucleus gives nuclei. So definitely where I'm going to center my teaching is this particular place here. So in the course of this, now the idea of this radioactivity was first observed by Henry Becquerel. So Henry Becquerel was the first man to have observed this, after which 2 years after, two people, husbands and wife, Mary and Pierre Curie, then demonstrated using this man's observation. You understand? Exactly in 1896, this one here observes that the nucleus of an atom breaks. You understand? So that's not where I'm going to. Now, what you need to understand is that anytime the nucleus of an atom breaks, two things are happening. Number one, particles are emitted. Alongside energy is released. So the two things that are happening are particles are produced, energy is released. Now there are three types of particles in this case. One of which is we have the alpha, we have the beta, and we have the gamma. So and this will lead me to answering this particular question. First of all, I need to tell you the characteristics of each of them, after which I will answer this question. So three particles are emitted during radioactivity, one of which is the alpha, beta, and the gamma. Now, I'm going to tell you the characteristics of each of them, after which I will answer that question. Now, for the case of the alpha particles, they are positively charged. One. Number two, the alpha particles are represented with helium nuclei, atomic number 2, mass number 4. So anytime you see this in a nuclear reaction, the first thing that comes to your mind is that an alpha particle has been produced. Now another thing is the alpha particles, they have short wavelengths, they have high ionization energy, they have low penetrating power, they can be stopped or absorbed by thin sheet. That's not where I'm going to. Now, where my point of emphasis is that the alpha are represented with this. Take note of that. Now, for the case of the beta, if you are familiar with the characteristics of this, definitely you can answer the characteristics of this remaining two. Because I'm going to use the characteristics of this one to prepare these two here. Now, in this one, I said these ones are positively charged. In the case of beta, betas are negatively charged, and they are represented with electrons. Atomic number -1, mass number 0. They have shorter wavelengths. They have penetrating power, they have ionization energy. Intermediary to alpha and gamma, in the sense that their ionization energy is lesser than that of alpha, but greater than that of gamma. The first thing is they can be stopped or absorbed by aluminium sheets or aluminium plates. Then in the case of the gamma, those ones are electromagnetic. They don't have a sign. You understand? They don't have the way of representing them. That's why we say they are electromagnetic. They are in the form of wave. Now, another thing is, so in the course of balancing this now, so let's be on the lookout for atomic number. So I have 88 as the atomic number in the reactor. So what about the product? I have 86 and 82. That's an 88 too. So I guess the atomic number in both product and reactant seems to be balanced. But if you be on the lookout for the mass number in the reactant, here I have 226. Here I have 4. Because I know alpha are represented with this. So I can replace the whole of alpha with something like this. So how many more is needed to make this equal to this? Because our aim is to make sure by the time I have this one and this one together, I get a 226. That means if I had x and 4 together, I must get a 226. These two here must be balanced. So that x will be 226 minus 4, and that x is 222. Or just see, what will I add to 4 to make it 226? That's 222 now. So the value of x in this nuclear reaction is 222. Now there are other questions. Questions like if I have 235 uranium 92 plus a neutron to give 144 billion 56 and 90 krypton 36 plus 2x. What is the value of x in this nuclear reaction? So how are we going to get the value of x? The same idea. Just think of what I have told you before. Just balance. By the time I had the atomic number, so this is a nuclear reaction too. So this one is an artificial radioactivity. This is artificial breakdown. So this is particularly nuclear fission. So fission is the breakdown of a very heavy nuclide when you bombard them with a particle such as neutrons. So that's not what I'm going to. So in the course of balancing this one, what do I need to do? I have 92, 0 is 92. 56 and 36 is a 92 as well. So I guess this one here is balanced. I'm looking for the value of x, don't forget. I'm looking for x. After which, by the time I had this one and this one together, 235 plus 1 is 236. I have 144 plus 90 is, 235 plus 1 is 236. So that this one plus this one is what? A 234. So 144 and 90, you can experiment that. 144 and 90 is 234. So that means how many more is needed for this particular one here to be 236? Because your aim is to make sure, since this one is 236, then by the time you have everything here, they should sum up to 236. So in the course of doing that, let's see what I can do. I have 235U92. And to give 144, 90 then I have 2x. So let's see what x is. Now here, I said how many more will you have to 92 to get 92? You said 0, have it? Now how many more will I have to 234 to get 236? I needed 2 more. But don't forget, this one tells you that there are the value x here appears twice, more or less like. So first of all, there's something I need to chip in here. I have this. Don't forget, I said the atom of an element is divided into nucleus and electrons. After which the nucleus is divided into protons and neutrons. So how do I represent this particular thing? Or which other name can I give this particular one? Don't forget, proton is an isotope of hydrogen. You are familiar with this now? When I have something like this, or something like this, either this or this, yes, either this or this. You understand? This is an isotope of hydrogen called protium. Are we together? Then this is another isotope of hydrogen called deuterium. You understand? And we have a third isotope of hydrogen called tritium. So don't forget, protons, they are represented with something like this. Either 1, P1 or anything. You understand? So this is proton. Then for neutron, this is neutron. 1, then for electron, I've shown you electrons before. 0 minus 1. So you must get used to all these concepts now. So in the course of answering this, I have 236, I have 234 here. So I needed 2 more to balance that one. So by the time I had the 1 here, don't forget 2 times 1 is a 2. And 144, 90 and 2 is a 236. That means this particular reaction is balanced. So thank you very much for watching. God bless.